Dear students of radio wave propagation, our lesson today is about non-flat earth propagation. Propagation when the earth is non-flat. We want to find this is the maximum vertical variation of the surface of the earth, and we want to find the limit when the earth is considered to be flat or smooth as seen by the incident wave. The propagation constant of the incident wave is k0, and the angle made between the incident wave and the horizontal is psi. This angle is psi. And the maximum variation in the earth is delta z. The vertical component of the propagation constant here, this is the vertical component. Propagation constant is directed in this direction here. The vertical component here, which is kv, k vertical, equal to k0 times sine psi. As we can see here, it is k0 sine psi. And the vertical component is 2 pi over lambda v. Lambda v is the wavelength of the vertical component. We write here k0 equal 2 pi over lambda naught. 2 pi over lambda naught. Cancel here 2 pi with 2 pi. And from this equation, lambda v, if you invert this fraction, lambda v is equal lambda naught over sine psi. So this is the vertical component wavelength in terms of the total wavelength, lambda naught in free space, over sine psi. For the earth surface to be considered smooth, the vertical wavelength should be less than the vertical variation should be less than 0.1 of the vertical wavelength. In this case, the surface will be considered smooth. We will use this equation. Now the phase variation due from this point to this point, the phase variation due to the vertical variation in the earth is equal to 2 delta z, because we have here delta z here and delta z here. Delta z to go down and delta z to go up. And k vertical, this is k vertical, which is k0 times sine psi. This is the total phase variation. Now we want to calculate the total phase variation when delta z is equal to lambda vertical over 10. Okay. We put here, this is delta z, maximum delta z. This is delta z. Maximum. Delta z maximum, lambda v over 10. And this is k vertical. This is k vertical. K0 times sine psi. And lambda vertical itself is equal lambda naught over sine psi. When you put lambda lambda naught over sine psi. Okay. K naught is equal to pi over lambda naught sine psi, and this lambda v over 10. Now lambda v is equal lambda naught over sine psi. Therefore lambda v over this will be lambda naught over sine psi is equal lambda v. Therefore this will cancel with this. And here we will have 4 over 10.4 pi. the result, the maximum phase variation when the Earth is considered to be smooth is 0.4 pi radian, of course radian. This is an example to illustrate the idea. The frequency is 100 megahertz and the wavelength is 3 meter, because lambda naught is equal, the velocity in free space is c, speed of light, and here the frequency. The speed of light is 3 times into 8 meter per second over the frequency, which is 100 megahertz, 10 to 8 hertz. Result is 3 meters, 3 meters, as can be seen here, lambda naught. Therefore the maximum delta z is lambda v over 10, and lambda v is equal lambda naught over sine psi. Okay, and this lambda v over 10. Lambda naught is 3 meter here, and 10 is as it is, and here when psi is very small, sine psi is equal approximately psi 4 in radians. Okay. From this equation, okay, lambda v is equal, as we said, this is equal to psi is given here to be 2 degrees, and 2 degrees, when we convert it to radian, we multiply by pi and we divide by 180. The result is 2 over 60 radian. We substitute for psi here, so 2 over 60 here, 2 will be in the denominator and 60 will be in the numerator, because it's in the denominator here. Lambda naught is 3, this lambda naught 3 is lambda naught, and 2 over 60 is psi or psi, and 10 is as it is, 10. The 0, you take it out with the 0, and this is 6 over 2 is 3, 3 times 3 is 9 meter. At this frequency, the result is that at this frequency, 100 megahertz, even a large variation in the surface, vertical variation in the surface of the Earth of 9 meter is considered to be smooth. After 9 meter, it is rough. Lower than 9 meter, variation is considered to be smooth. Now we move to the effect of change in the index of refraction in the air, because we are surrounded by the atmosphere. The atmosphere is not free space, and as we know, the standard atmosphere, for a standard atmosphere, the density, the air density, will decrease as we go up, as the altitude increases. Therefore N1 here, if we divide the atmosphere into layers, small thickness layers with small thicknesses, this, the first layer is N1, the second layer is N2, N3, N4, etc. N1 is greater than N2, or N4 is less than N3, N3 is less than N2. As we go up, the density of the air will decrease. Since the density will decrease, the refraction here, the angle of incidence is theta 1, and theta 2 will be greater in the less dense medium, and here it will be greater. The angle of incidence is measured between the incident wave and the vertical to the interface. As we can see, the wave will not move in a straight line. In a straight line, it will move like this. It will not be. It will be concave down. Okay, so as we said here, n1 is greater than n2. This is refraction index. Now the horizontal component of the wave will be equal at the interface here. The horizontal component is equal, as you can see, it is k here, kn times sine theta I. And the next layer is ki plus 1, k1, then k2 times also sine the angle here, sine the angle. Therefore ki sine theta I equal ki plus 1 sine theta I plus I is the atmospheric layer, small layer with small thickness, we designed it, and ki plus 1 is the higher layer. Now ki is equal k naught times root epsilon Ri, because as we know from electromagnetic courses that k integral is equal for any medium equal k naught for a free space times square root of mu r epsilon r. And since the atmosphere does not have magnetic properties, mu r is, we end up with k equal k naught root epsilon r, Ri of course, and here I plus 1. From this equation, of course, the n is root epsilon r. This is the definition of the refraction index. It is root of the relative permittivity of the medium. Here, square root of epsilon Ri is ni, and the square root of epsilon Ri plus 1 is ni plus 1, and here we have sine theta I, and here sine theta plus 1. When ni plus 1 is less than ni, because ni plus 1 is the higher layer, and the refraction index will be lower because the air density will decrease, then theta I plus 1 will be greater than theta I, as we have already seen here. The theta will increase and the wave will move like this. The wave will not move in a straight line. It will move like this. Of course, the curvature will be much less than that, but we just to explain. But for long distances, you will have significant effect. This is the idea here. It is difficult for if each time you want to make a design for a microwave or a radio wave link to make these refraction calculations. To avoid this situation or to avoid this problem, the effective earth radius was invented or was proposed. The effective earth radius is equal to this value. It is 8,497 kilometer. 8,497 kilometer. This is for standard earth. The idea came as the following. This is the earth here, okay, and this is the wave. The wave will propagate something, instead of it will propagate something like that. It is not straight, of course. Now to make this line straight, if we increase the radius of the earth, the actual radius of the earth, if we increase it, and at the same time we increase the radius of this circle, let's see this part of a circle, until it will be straight line. So we need to increase the radius of the earth until this will be straight line. the increase will be this. I remember it is 4 times the actual radius of the earth is I remember it is 6. It is, I think, 0.75 of this value. Let me calculate it here. See the calculator. Okay, it is 8,497 times 0.75 is equal. This is the radius of the earth. Actually, 6,373 kilometer. If you multiply this is the actual. If you multiply this by the factor of 4/3, you will obtain this radius. It is 8,497. Therefore, according to this, the effective radius of the earth is 4/3 times the actual radius for standard earth atmosphere. In some areas, the atmospheric conditions will not be standard because of the weather variation. Anyway, we will use this number for our calculations. We will consider that the radio waves are straight lines when we use effective earth radius instead of the actual radius. Now we want to find the maximum horizontal line of sight range. Maximum horizontal line of sight range. We have here, we have this antenna, and this is the tower of the antenna, the height. This is the tower, and this is the receiver. Okay, and here this line is the propagation. It's straight line. Because why it is straight? Because I think it should be like this. Okay, let's take it like this. Okay, here it is tangent to the earth at this point. Yeah, I will increase this to be like this. Almost. Okay. H1 is the height of antenna 1 and H2 is height of antenna 2, and they are communicating. The maximum distance the two antennas can be apart is determined by, we want to find the equation that governs this. If we move this antenna away, further away, there will be no line of sight. The maximum distance is when it is tangent. When the distance between the two antennas is closer, they will be in line of sight. If they are further away, they will not see each other. Now r squared, this from Pythagoras rule or law theorem, this r squared is equal, this is squared minus this is squared. This squared is h1 plus ae squared minus this is ae squared. ae squared minus ax squared is 0, and we will have 2ae h1 plus h1 squared. Since h1 is much less than ae, the antenna height is much less than the radius of the earth, of course. So we can cancel this. We can approximately set this to 0, approximately 0. This is approximately 0. And the equation here will be r squared equals twice ae h1. R is approximately equal to dt. It's not equal to dt. It's approximately equal to dt. We will consider that r is equal approximately to dt. Therefore, r is square root of this. If you take the squared, here you have square root. and r is dt is equal to square root of twice AE times h1. Therefore, the maximum distance you can place an antenna is equal to this. The total distance would be the summation of dt1 and dt2, of course, as you can see here. The maximum distance, this distance here is equal square root of twice AE h1, and this distance is equal to square root of twice AE h2. The total distance from here to here is this equation. This in meters, and this should be in meters, and this should be also in meters. So this is called, this distance is called the maximum horizontal line of sight range, dm, d maximum. As you can see here, it is dm. Okay. For line of sight communications, space wave, dm, as we mentioned in the earlier page, square root of twice AEH1 plus square root of twice AEH2. Now we have these ranges. For a free space zone, the distance should be given by this equation. D max is given by this equation to be considered the free space zone. This means that the Earth has no effect. If the Earth has no effect, only space, the distance, maximum distance, should be between 0 and D max. D max is h2, the height of the receiving antenna, tan 5 degrees, and the square root of h2, height of receiving antenna, tan 5 degrees, h2, and h1 is the height of the transmitting antenna. In this case, very a small portion of the radiated wave will reach the Earth, and the reflection and diffraction will be negligible. That's why we consider it to be free space. Okay. For a flat Earth interference zone, where the equation used was, if you remember, it was the path gain factor twice absolute value of sine k naught h1 h2 over d. H1 is the height of the transmitting antenna, h2 height of receiving antenna, the distance between transmitting and receiving antennas, and k naught is the propagation wave factor. D should be greater than d max here, and should be less than 0.3 dm. dm is this is dm. dm is given by this equation here, dm, the maximum line of sight range. Now, for curved Earth interference zone, even if the distance is greater than dm, there would be communication because there is diffraction. D is between 0.3 dm and 0.75 dm. For tangent ray zone, it is D is between 0.75 m. We continue until 1.25 dm. Diffraction zone is greater than 1.25 dm. Okay. An example here on flat Earth. The frequency is 937.5 megahertz. The height of the transmitting antenna is 16 meter, and the distance between the transmitting and receiving antennas is 2 kilometers. Find the receiver heights for maximum received signal. We want maximum received signal. Find the receiver height, h2. We want to find h2. Find h2 for maximum received signal. We want the signal level, the signal power, to be maximum. So where shall, at a distance of 2 kilometer, what should be the height or the heights or the minimum height which would give us maximum received signal? The received signal, as we know, is proportional to F over D. F over D, path gain factor over distance. Now f is equal to sine 2 pi h. This is as you can see here, this is the same equation, k naught h1 h2 over d. Instead of k naught we wrote 2 pi over lambda naught, so it would be 2 pi over lambda naught h1 h2 over d. As you can see here, 2 pi over lambda naught, this is h naught, k naught, sorry, is k naught h1 h2 over d. And maximum, the reception will be maximum when sine is equal to 1, therefore the maximum is 2. The sine will be 1 because this cancels with this will be 1. Sine will be 1, the sine is 1 when the argument, when the angle here is equal pi over 2 plus n pi, where n is equal 0, 1, 2, 3, etc. This is here when the angle is here, you have pi over 2 plus pi, it will be minus pi over 2 plus pi, it will be pi over 2, and so on. That's why we have this equation. The wavelength is equal the speed of light in centimeter per second. This is centimeter per second, and centimeter per second over the frequency. The frequency is 935 megahertz. The frequency. Mega is 10 to 6. This is hertz per second. This is hertz, which is per second. Per second, cancel with per second, and you will end up with this 32 centimeter wavelength. Now H2 from this equation here, you can find H2 because H1 is known, the distance is known, wavelength is known. The only unknown is H2. For H2 is given by this equation now. It is 20 times 1/2, which is 10 plus 20n. We can place the receiving antenna at a height of 10 meter or 30 meter or 50 meter or 70 meter, and we can obtain the same signal level. We can choose what suits your situation. Here is another example. But I will continue later on. If you have any comments, any questions, please let me know. See you later on. And thanks for listening and for understanding.